All right, so in nuclear reactions, if we've ever seen a video of a atomic bomb being detonated, you can see the huge mushroom cloud. If we think about nuclear power, it supplies a tremendous amount of energy, and the reason for it is going to be because these nuclear reactions themselves um, are going to involve a tremendous amount of energy, and it's going to be related to the equation E is equal to mc squared, where m is just the mass, c is the speed of light, so 3 times 10 to the 8th meters per second. So even if we have a very small mass, if we lose that amount of mass in a nuclear reaction, it's going to be associated with that huge energy change. And when we think about chemical reactions, there is a change in energy. So endothermic is absorbing energy, exothermic releasing it. But in comparison to the nuclear reactions, those chemical reactions are going to be extremely small in terms of energy, either released or absorbed. And if we look at the example of uranium-238, so if we have 1 mole of uranium-238, 238 grams of it, and allow it to decay, the mass lost through that process is going to be 0.0046 grams, so a very, very small amount. But if we think about that equation, delta E is going to be equal to the change in mass times the speed of light squared. And note with this one, since we want our answer for energy in joules, we need to have the mass in kilograms. So that's why we've got negative 4.6 times 10 to the negative 6 kilograms here, rather than just 0.0046 grams. That's just the unit for joule is kilogram meter squared per second squared. But because the speed of light is so large and we're squaring that value, even though we've got a very small mass here, it's going to be associated with a tremendous energy change. And this, again, is going to be the basis for nuclear reactors in nuclear energy, for the massive power of nuclear weapons as well. So if we look at one more example here, we want to figure out how much energy is lost or gained when 1 mole of cobalt-60 undergoes beta decay. And the mass of cobalt-60 going to be actually just under 60, so 59.933819. And that's going to decay to nickel-60. So you can see the mass here decreases slightly, 0.003, whatever it's going to be there. So in order to figure out the energy change, we need to get the exact mass loss here. So we'll just subtract those two, get a mass loss of 0.003031. And with this, since the mass is less at the end, we'll have a negative value when we plug it into the delta M spot of this equation. And then again, we're going to, oops, I didn't put the square here, but we're going to square that speed of light, ultimately giving us about 3 times 10 to the 11th joules being released during this process. So again, a tremendous amount of energy since we've got 10 to the 11th. So we can think of that as 298, and then we'll have 9 zeros after that. So a huge, huge number there. I think that would be 298 billion, I believe that's what that number would be. And then with this, oops, let me get rid of that too. With this, we have what's known as the nuclear binding energy. So when we take those individual particles and actually bind them together in the nucleus, there's going to be the mass defect. So if we think about a simple helium nucleus here, the individual subatomic particles in that nucleus, so helium-4, 2 protons, 2 neutrons, going to add up to a little over 4.03 atomic mass units. But then when we actually take them and combine them in the nucleus, we only get a mass of just over 4, so 4.0015. And again, the difference between those two is just going to be the mass defect. So if we wanted to think about the energy that's going to be associated with that process, we can again do the exact same thing here. In this case, we've got a slightly different rounded speed of light, 2.9979 rather than just the 3. But it's the same idea, converting the mass from grams to kilograms, just so we get the correct unit there. And then we can express this on a per mole basis. Because if we think about if we had 1 mole of helium, the mass loss would be this much per gram, or per mole rather. And then with it, we can also think about a single atom. So if we had a full mole of it, this would be the energy change. But if we just had a single atom, we can use Avogadro's number, divide it by 6.022 times 10 to the 23rd, just to get the joules per atom. And then if we think about that nucleus even further, it's got 4 particles. So if we wanted to think about the energy change for each of those different nucleons, so the protons and the neutrons, we can then take that number and divide it again, this time by 4, just because we'll have the 2 protons, 2 neutrons in that nucleus there. And then with this, in order to actually utilize it, we need to have the way we utilize it, I guess, is going to be in the nuclear reactors of those power plants or in the atomic bombs. And when we're looking at it, we've got two different specifically ways this can kind of occur. So we can take the fission, in this case, is going to be taking a larger atom and essentially hitting it with a particle like a neutron and splitting it into smaller ones. So this is going to be the reaction that gets done in the nuclear reactors at power plants. So we're going to take uranium-235, bombard it with a neutron, and then we can have either of these 2 reactions occur here. So you can see either barium, krypton. Well, that would be the bottom one, but we could have also had, excuse me, tellurium. Okay. So we could have barium and krypton be the products. We could have tellurium or zirconium be the product. But either case, we can see it's going to be a very similar reaction. And then with each of them, just notice that the sum of the atomic masses still add up to what we started with. Same thing with the bottom reaction here. So both of them add up to 236, or the atomic number on the bottom add up to 92 for each of them. So we're still following those rules for nuclear reactions. But to kind of see what's specifically occurring there, because we don't just have one single reaction, we're going to take that neutron, hit that's unstable nucleus, so that radioactive nucleus, and then it's going to break down, and we're going to see this is going to lead to a chain process or a chain reaction. And the reason for this is because, and if we go back for a second, if you notice here, either of these reactions, so tellurium and zirconium, barium and krypton, we're forming those new elements, but we're also releasing neutrons. So what we're going to see with these reactions here is we have, if we think about this as our uranium-235, we hit it with that neutron, breaks down into boron and krypton, whatever it's going to be, or barium and krypton rather. And then we also have these neutrons that are coming out. So these are going to then hit new atoms. Same thing with these neutrons. So we're going to have this process just be a repeating pattern. And that's why we're going to refer to this as a chain reaction. So with each of these, we would think of these rather than this being uranium and breaking down into barium and krypton, we would actually think of all of these yellowish atoms as uranium. And then from these, we're releasing those neutrons, which are then going to hit the next uranium, which is then going to release more neutrons, which will hit the next uranium. And in order for a nuclear reactor to be effective, we actually need this chain reaction to occur. So we can't just have it happen with a single atom or a few atoms. So we need a sufficient supply of these radioactive nucleus in that reactor in order for the chain reaction to occur. Otherwise, it just sort of fizzles out. And that's what you can see here. So in this case, we've only got a couple of these nucleus. So we hit the first one with the neutron, ejects a couple more neutrons, hits the second one, but then there's nothing else there. So the reaction effectively stops. Whereas in this case, we hit the first one with the neutron, releases a couple more, hit some more nucleus, and then we see that process occur even more. So that's going to be the chain reaction. But with it, actually, I'll get to this one first. With it, to prevent it from getting too out of hand, we've got what are known as control rods. So if you think about this picture here, you can see the whatever color that is on the bottom. These are going to be the fuel rods that actually contain that uranium. But then in between them, we're going to have the control rods, which makes sure that this reaction doesn't get so out of hand that it effectively causes sort of a meltdown, a catastrophe at the nuclear power plant. So the control rods are going to be important from essentially having the reaction go too fast, produce too much energy at one time. But to go back here, this is going to be just a general schematic of how the nuclear reactors work. So if we look at it, you can see here the reactor core. So that's where we've actually got the fuel rods. We've got the control rods mixed in there as well. So that's going to be where we have the reaction taking place. And then we're going to have the heat produced going to be tremendous. The way we actually utilize that heat is by having it heat up water, produce steam, and then that moves a turbine. So if you see here, we've got the water, we're producing steam that's going to travel through here, and then we move the turbine to produce that electricity. And then one other thing to note, and the reason why these nuclear power plants are often built near water is because they need a tremendous amount of water to keep them cool. So if you look here, we've got just some general river, but also notice that the river itself is 27 degrees in terms of the temperature of that intake. But then when the water is being dispensed out, because we're going to cycle it through, the water coming out of here is 38 degrees. So sometimes with these nuclear reactors, there's what's known as thermal pollution, where they're going to thermally pollute that water in the sense that they're going to heat it up. And in some cases, that can affect the ecosystem because we're going to have much higher temperatures there than we would through the rest of the water. And that can sometimes attract different organisms. So fish or whatever's living in that water prefer the warmer temperatures. They'll see a sort of an aggregation of those organisms near the outtake here, just where we've got that warmer temperature. And then typically it's not too much of a concern. But I remember recently, actually, in New York, there's the Indian Point power plant that's a little bit north of New York City. And with the water they had, so it was eventually radioactive because it was tritium, I believe, so hydrogen-3. They have to store some of the radioactive water for a certain amount of time, allow it to decay, so it's not as radioactive. But they were doing what their plan was, and I think they went through it, was actually taking all of the radioactive water, the tritium-3, and just dumping it in the Hudson River because they were just counting on dilution, essentially. So a huge amount of water already in the river. So if we dump a relatively small portion of radioactive water, it's going to get diluted, not really going to cause an impact, which might be true in some cases, might not be the best in others. So with the nuclear energy, of course, it does offer a alternative to fossil fuels in the sense that during this process, we're not combusting fossil fuels, we're not producing carbon dioxide, we're not producing those greenhouse gases. But there are greenhouse emissions associated with building the power plant. There are, of course, the radioactive waste aspects that have to be dealt with as well. So with the nuclear energy, it is I think overall a positive development, positive technology, but there are, of course, issues that have to be addressed as well. And then part of the nuclear waste, at least now, they can take that nuclear waste, and then rather than just dumping it in a giant barrel, putting it underground, they can vitrify some of it, meaning that they can actually sort of trap some of that nuclear waste in glass. So it makes it a little bit safer than the traditional kind of just like barrels of nuclear waste. But with that one, it was looking at fission. So we were taking those atoms, breaking them down into the smaller ones. A sort of opposite process is going to be fusion. So in this case, we're going to be taking smaller atoms and essentially jamming them together to make larger ones. And this would be a better alternative in terms of energy production if we could have it occur. So if we could have cold fusion happen, so fusion occurring at like room temperature, that would be a beneficial energy alternative because in this case, we're not going to be producing radioactive waste. So the products of these aren't going to be nuclear or aren't going to be radioactive. This actually occurs in stars. So like the sun itself has high temperature, high pressure in the center, so we can have fusion occur there. Um, and you may have heard in the news, I think it was in December, there was a positive result in terms of a fusion experiment. But even with that one, they used a laser to kind of kickstart the process. And the laser itself had a tremendous amount of energy. So ultimately, it wasn't a net increase in energy from the point of the fusion perspective they had it occur, but there was a huge supply of energy to kind of get that started. So they're working towards potentially being able to utilize fusion as an energy source. But I still think it's going to be a very, very distant trying to think of the one. I just don't think it's going to be a development that'll yield any true uh, benefits to the general population anytime soon. So I think at the moment, we've still got to focus on either using the nuclear energy we have with the fission reactions or switching to more hydropower, solar power, wind power, things like that. Because I think that the fusion is still pretty far off there. Because the reason is typically fusion has to just occur at a very, very high temperature. So if we have to heat something up that much, it's just not going to be energy beneficial in that sense. And then you can see here, this is just one sort of setup that they can use to try to have this process occur. And in this case, they're using magnetic fields in order to heat the material. But again, with fusion, cold fusion, so we could have it happen at room temperature or relatively low temperatures, would be the ideal energy source. And then with this map here, we just got a map showing the radon concentrations. So radon is going to be a radioactive gas. Ultimately, it's going to have 86 protons, I think. Yeah, atomic number 86, so 86 protons. So typically, it's going to decay, or you'd expect it to decay via alpha decay. So one of the reasons this can be so problematic is because the radon itself, like the rest of the noble gases, and like the noble gases would suggest, is going to be a gas. So it's going to be something that we can breathe in, but it's emitting alpha particles. So if we ingest the radon and then it emits the alpha particles when it's inside of our body, then those particles can do damage. You think about those positive helium nuclei are going to be really good at gaining electrons. So if we have those alpha particles in our body, the alpha particles are going to steal electrons from different things. They're going to damage cells and different processes. So with radon, typically what it's associated with is going to be relatively high amounts of uranium in the soil because the uranium itself is going to degrade into radon. So I remember in Utah, there were certain areas where radon was something they were particularly worried about, just because you can see here with the red, there's a couple of those counties that have the highest predicted average of indoor radon. And again, it's just going to be because those areas have a relatively high amount of uranium in the soil. And then you can see there's a pretty good stretch that kind of goes from parts of the Pacific Northwest, so just the very corner of Washington out east, throughout the Midwest, the Rockies, all the way to portions of the Northeast as well. So you've got a kind of a swath of land right there. But then in terms of the South and the West, not as big of a concern in terms of the radon indoors. But with it, there will be a couple other videos to kind of just look at, particularly the Hanford site. So a site in Washington that was actually used for the production of plutonium during the Manhattan Project. So they used the plutonium in, I believe, one of the bombs that was dropped on Japan, as well as the first testing of the atomic bomb, the Trinity test. So in New Mexico, I forget where Los Alamos is in New Mexico. But Hanford site was like I said, the site that produced that plutonium. And then it's one of the most toxic sites in the country. It also displaced, kind of was just put in the center of some of the indigenous tribes within Washington. So the Hanford site, I believe, is about in this location. So it's out east, but not fully out east, if I remember correctly. And then there was a similar site in Oak Ridge, Tennessee. Forget exactly where Oak Ridge is in Tennessee, but they were focused on the production of uranium. And then both of those elements, plutonium and uranium, were used in the atomic bombs, used in nuclear reactors now for the power plants and things. So there'll be a video related to Hanford, as well as a video related to the atomic weapons and nuclear energy.